Okay, in this section we're going to talk about some numerical summary measures, some of which I'm sure you've heard of at some point, others which you may have heard of but not be familiar with. We just want to make sure everybody's on the same playing field as we go into this. We're also going to start the discussion of something we'll be talking about throughout the rest of the course, is sample estimates versus population measures, and we'll define what I mean by that in this section. So if we want to summarize and or describe a set of continuous data, there are some things we can look at. We can try to measure the center of the data via a single quantity, such as the mean or the median of our data. We can also try and measure the spread or variability in our data by using something called the standard deviation, or its synonymous quantity, the variance. Or we could look at the range of the data, the largest value minus the smallest, to encapsulate the spread. So let's just start with the basics of the sample mean, the average, or the arithmetic mean. Given a set of data, the general recipe for computing a mean is to add up the data and divide by the sample size. Most of you are probably familiar with that. And the sample size, we call it n, is the number of observations or pieces of data in our data set. So, for example, suppose I had a sample of 5 systolic blood pressures from a population of subjects. I only have 5 pieces of information, and they were 120, 80, 90, 110, and 95, and they were in millimeters of mercury. So, of course, in statistics and in mathematics in general, we like to take ideas that everyone can understand and obfuscate them with notation. So I'll show you how we do that. I promise that won't be a huge part of the course, but I want to let you know how you'll sometimes see represented and empower you to get through the jargon here. So we could represent these values with variables x1 through x5 to represent 5 different pieces of information from a larger population, where x1 was 120, x2, 80, etc. Well, the sample mean is easily computed by adding up these 5 values and dividing by 5. In stat notation, the sample mean is frequently represented by a letter with a line over it. For example, this x with a line over it, pronounced x bar. So here's the mean, the sample mean of these 5 systolic blood pressures. We just take those 5 numbers, add them up, and divide by 5. We get a sample mean of 99 millimeters of mercury. More generically, and the reason we sometimes put things in terms of variables like the x's instead of numbers all the time is then we can generically present a formula that can be used in all scenarios. And here's the generic representation of the formula for the mean. It says that x bar is equal to this sigma of x of I indexed from I equals 1 to n, that's the Greek letter sigma there, all divided by n. So that top letter is just math notation. The Greek letter sigma in capital version is called the summation sign. And this is basically, it's kind of a sexy shorthand way of saying add up all the observations from 1 to n. So if we had 5 observations, that would be indexed I equals 1 to 5, and we'd add up x1, x2 through x5. That's just a shorthand way of saying add up the 5 measurements. The sample mean is also called the sample average or the arithmetic mean. One thing that's important to note about this, and we'll talk about later again, is the mean it's a great measure of central tendency, but it is sensitive to extreme values. One data point can make a great change in the value of the sample mean, especially in smaller samples. Why is it called the sample mean? And that's to distinguish it from something called the population mean, the thing we really want to know but can't get, so we have to estimate it vis-a-vis an imperfect subset of observations from that population, and we'll talk more about that at the end of this section. Another measure of central tendency that you may have heard of is the sample median, or the median. The median is basically the middle number, sometimes called the 50th percentile. And other percentiles can also be computed as well, and we'll talk again about those in a later lecture, but they're not necessarily the measure of the center of the distribution. So basically, how do we compute a median? If we were doing it by hand, we'd take our values and arrange them in order from smallest to largest, pick the one in the middle. So here are my 5 values ordered from smallest to largest. And you see the number 95 is smack in the middle of those 5. So my sample median is 95 millimeters of mercury, which is slightly lower in value than the sample mean of 99. One nicety of the sample median is that it's not so sensitive to extreme values. For example, if that largest observation was 200 instead of 120, the median would still be 95, but the sample mean would increase from 99 millimeters of mercury to 115. So in statistical terms, the median is more robust to extreme values than the median. It can suffer the blow from them, whereas the mean sometimes acts funny. What do you do if there's no obvious middle of your data? Well, if there's 5 data points and you order them, the third data point is the middle. But if you have 6 data points, for example, which was in the middle? There's not an easy middle to pull out. Well, if the sample size is even, what you do is you take the 2 middle values, if you will, and average them. So if we had 6 observations that look like this, then our median would be after ordering them from smallest to largest, the median would be the average of the third and the fourth observations. Okay, measures of central tendency like the median are informative, and actually having both gives more information than either alone, and we'll talk more about that further down the line. But another thing we're generally interested in looking at continuous data is how spread out, how variable the data is. There's different ways to measure variability. What we're going to talk about here now are 2 quantities that are related to each other by a simple function, what's called the variance and the standard deviation. And the first thing we're going to talk about is the sample variance, the quantity we can estimate from our data at hand, whereas again the population variance exists, how variable all the values in the population are, but we can only estimate that based on an imperfect subset of values in our sample. And basically, the formula may or may not look intimidating, especially if you haven't seen math in a while, but it's actually not that painful. Let's look at what's going on here. S squared, which is the symbol we use for sample variance, because S stands for standard deviation, and the variance is the standard deviation squared. What we do is we actually take the distance between each observation, each x sub I, if you will, where I ranges from 1 to n. We take the difference of each observation from the same sample mean, the sample mean computed on all observations. We square each of those distances and then we add them up. That's what the sigma is there for. So basically the numerator here is the cumulative squared distance of all observations from the sample mean. And then we divide that by n minus 1. Forget about the minus 1 part for now. Think of it as n in your head for a moment. What is this quantity? It's basically the average squared distance of each point from the sample mean. So it's a measure of average distance, right, in squared units. What we do to get the sample standard deviation is we take the square root of this quantity and basically get the average distance. So basically, variance is a measure of square distance. Standard deviation is a measure of distance in the original units of the data. So it's the average distance that any single point in our sample falls from its center as measured by the mean. The larger this number, the more spread there is in our data. So again, recall the 5 systolic blood pressure measurements we had before with the sample mean of 99 millimeters of mercury. Here they are again. Well, if we were to compute the standard deviation in this sample of numbers, what we'd first do is add up the difference of each of those values from 99, square it, and add those up across all 5 values. So that we take the first value, 120, subtract 99, square that, then the second value, 80 minus 99, square that, etc. And if you carry the math through on this and work it out, this total sum turns out to be 1,020. What is the units of measurement here? Well, think about this. Each observation is in terms of millimeters of mercury. The sample mean is in terms of millimeters of mercury. So the difference between each observation and the sample mean is in millimeters of mercury. And then we square that. So the units of this squared difference are millimeters of mercury squared. 1,020 millimeters of mercury squared. So now what we do is we basically average this with a slight caveat. Instead of dividing by n, we divide by n minus 1, and I'll talk about that in a minute. We average the squared distance. So we take 1,020, the cumulative squared distance, divide by n minus 1, 5 minus 1, which is 4, and we get an average squared distance of 255 millimeters of mercury squared. Now, to get this in units that we're used to and can physically ascribe or think about, if we take the square root of that variance, we get the square root of 255, which is roughly 16 millimeters of mercury, and that's our standard deviation. On average, the average blood pressure measurement in this sample falls 16 units, 16 millimeters of mercury from that mean of 99. This is nothing more than a measure of distance in the units of the original data. So the bigger the sample standard deviation is, the more variability in our values there are. This thing again measures the spread of observations about the mean. It can only be 0 if there's no spread, i.e. all our observations have the same value. The units, again, of the standard deviation are in the same units of the original data. For example, our standard deviation here was in millimeters of mercury. The units of the variance are in that measure squared. This will often be abbreviated, including within this course, as with a capital SD. Can you guess what that stands for? Or a lowercase sd. S squared is the best estimate from the sample of an underlying population quantity, the variance, which we frequently represent with the Greek letter sigma squared. And S is the best estimate of the population standard deviation, sigma. So what again do I keep meaning by population and sample? Well, let's formally define this. The sample will always, for our purposes in this course and for most of the work you'll be involved in or be privy to reading about, it will be based on a sample, which is a subset, a portion, a part of a larger group's population, or sometimes called a process, from which information is collected to learn about the larger group. So, for example, a sample of blood pressures from 5 18-year-old male college students in the United States. Well, we only have 5 pieces of information collected from a larger body, all 18-year-old college students in the United States. A population is the entire group for which the information is desired, the one from which we've selected that subset called a sample. So in this example, we have a sample of 5 blood pressure measurements from all 18-year-old male college students in the United States, and the population of which we're studying vis-a-vis that sample is all 18-year-old male college students. For studies, and in general, it is optimal if the sample which provides the data is representative of the population under study. This is not always easily done, and we'll talk more about that later in the course. However, in this term, we will make this assumption unless otherwise specified. Just to give you an idea of how we can go about doing this, and we'll talk more about this in the second part of the course, one way of getting a representative sample is called simple random sampling. This is a sampling scheme in which every possible subsample of a given size from a population is equally likely to be selected. So if we selected a simple random sample of 5 18-year-old college students and collected their blood pressure, the idea is that any subset of 5 was equally likely to be chosen by the random sampling method. Now, how do you do that? Well, we'll get into more detail in the second half of the term, but you could think of a names in a hat idea, where if you could write down the name of every 18-year-old college student in the U.S., put each of those names in a hat, shake the hat up vigorously, and pull out 5, you would get a simple random sample. Since we're only going to be able to work with samples which are imperfect measures, the best information we're going to get about the population is based on this imperfect subset through our sample estimates. These sample summary measures, the mean, the median, the standard deviation, are called statistics, sample statistics, and are just estimates of their population counterparts. Assuming the sample is representative of the population that we want to study, for example, it's randomly drawn, these sample estimates should be good, quote-unquote, quantities, good estimates of the true quantities. So here's the schema here. Shows our population with the big oval and our sample with the smaller circle. What can we get from the sample? Well, we can estimate a sample mean, that thing we call x bar. We can estimate a sample standard deviation called S. These are just estimates of quantities that exist at the larger population level. The true mean, sometimes represented with the Greek letter mu, and the true standard deviation with a sigma. Again, these are just estimates. We would like to know the population quantities, but we will never know it in the way we do research. So what do? We draw as representative sample as possible we can from the population. And we calculate the sample mean, x bar, to estimate the population mean. Is it necessarily the true mean? No. But we might be interested in, if this isn't necessarily the true mean, how good a guess is it? How close is it to the truth? And what we're going to learn, the statistical theory will allow us to estimate how close x bar, estimated from a single sample, is to the true mean that we don't know, using information computed only from the same single sample we use to estimate the sample mean. It's pretty amazing stuff we'll be getting into. Let's talk about the role of sample size on sample estimates, and we'll come back to this a couple times because this is important. Increasing sample size increases the goodness of sample statistics as estimates for their population counterparts. For example, sample mean based on a random sample of 1,000 observations is a better quote-unquote estimate mean than the sample mean based on a random sample of 100 from the same population. What does your intuition say? If I say I've got a sample mean based on 1,000 representative observations or 100, and you can have either one for a similar price, which would you take? Well, your intuition probably says the one based on 1,000. The same logic applies to sample standard deviation estimates. But what does it mean to be a better estimate? I want you to think about that and try and think about, what is your intuition getting at? Why do you think a larger sample, if you do, and if you don't, we can talk about that too, but if you do intuitively think a larger sample gives a better estimate, what do you mean by that? And we'll contrast that with what I mean when we get to the third lecture. One thing you should know, however, is that increasing sample size does not dictate how sample estimates from two representative samples of different size will compare in value. I may think that the sample mean based on 1,000 observations is a better estimate than the one based on 100, even before I collect data, but I can't say in advance which one of those sample means will be larger. In other words, a researcher cannot systematically decrease or increase the value of sample estimates, such as a mean and standard deviation, by taking larger samples. I can't guarantee that I get a smaller mean if I take more subjects. I can't decrease systematically my sample variation by taking more subjects. It may be larger than the estimate I get based on 5. It may not be. I don't know how it's going to compare until I actually take the sample. Now, to throw a rub into this and get you to think about it, it turns out extreme values, both larger and smaller, are actually more likely in large samples. So you might think that would impact what our estimates look like systematically. But think about this. So far as the mean goes, the smaller and larger extremes in larger samples balance each other out. And this balancing act tends to keep the mean in a steady state as sample size increases. It tends to stay about the same regardless of sample size. And there's no way to predict whether it will go up or go down with an increasing sample. In addition to these extreme values, non-extreme values, values closer to the sample mean, are also more likely in larger samples. And hence the sample standard deviation also stays balanced. It does not systematically increase or decrease with larger sample sizes. I can almost guarantee you that if you have sample statistics based on two samples of different size, they will not be the same estimates. They will differ in value. The sample means will not be equal. Sample standard deviations will not be exactly equal. But there's no way to tell in advance which sample will yield larger or smaller values for those quantities. This n-1, this is the first time you'll hear us talk about something, but not the last, called degrees of freedom. That's an oft-used term in statistics that people throw around without ever thinking about what it means. Well, one explanation for why this is called degrees of freedom, if we just added up the raw deviations of each observation from the mean, didn't square it, if we just added that up, any guesses what it would add up to? Well, some observations will be, mean is by definition sort of in the middle of the data. So some will come in below the mean, some will come in above, and they actually will average out to exactly 0. So if we added up the raw deviations and didn't square them, we get 0. So if I tell you the sample mean, right, and then I tell you the first n-1 values, the last one is fixed, right? So let me give you a trivial example. If I tell you I had a sample of 2 blood pressures, and the sample mean is 110 millimeters of mercury, and I say, now tell me the 2 blood pressure measurements that led to that mean, you'd be stuck. There's no way to figure out what the 2 values are. However, if I told you the sample mean was 110 millimeters of mercury, and the first measurement was 100, without me telling you the second, you can deduce and figure out that it would have to be 120 in order for that. Does that make sense? And that idea extends to larger samples. So once the sample mean is known, only n-1 of the observations can vary freely, so to speak. They could be whatever they wanted, but the last one is fixed, given that. So we lose a little piece of information. And this term degrees of freedom arises in other areas of statistics, and we'll see it again, and we'll talk about it again in the context for what we're doing. Why do we use the standard deviation as a measure of variation? Why don't we use, for example, the range of the data, like the maximum value minus the minimum? That might capture. That would be a good measure of variation at the population level where it's fixed. But it turns out, because of something I mentioned before, there's an unfortunate systematic link between the size of the sample we take and the values for the range we'll tend to get. Remember, the maximum and minimum, extreme values become more likely with larger samples, and as it turns out, under random sampling, the maximum tends to be larger with an increased sample size, and the minimum tends to be smaller. So extreme values are more likely with larger samples. And because the range only respects the extremes and doesn't take into account the additional likelihood of getting observations close to the mean as well, like the standard deviation does, the range will tend to increase systematically with increased sample size. And so we have something whose estimate is not invariant to the size of the sample we take, and we start to think that some problems in how we do research would be incurred if this value of our estimate were linked to the sample size. Okay, well anyway, means, median, standard deviations, all useful single number summaries, but they don't tell the whole story. For example, a lot of information about continuous data plays out in the role, the shape of the data and what it looks like if you graphed all observations. So in the next section, we're going to start talking about ways to visualize continuous data.